maybe tonight. So, I mean, for me, it's probably like mixed reaction, but I have one frustration that people couldn't answer most of them, only one or two answered correctly the short questions. The what is the register? I don't know why it was so hard, and people like bush around here and there and try to explain what register is. But it was one sentence in the PowerPoint, the PDF slides. And I mentioned many times that you need to write that and they'll get 100%. But I still give you a point. I didn't deduct point if even people bush around. I know you understand what register is, but you don't have the right sentence there from the book or from the PDF slide. So register was what? A small past memory inside CPU. So you push around like in around CPU or blah, 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 or memory, something like that. It's not, it's inside CPU. That's the word I was looking for. You have to say that. A small past memory inside the CPU. So that's the main definition of the register. Some people say 16-bit. That's wrong. A register is not a 16-bit. We have 32 registers in MIPS.
Sorry, sir, for joining late. This is Om present, sir.
Who?
Om? OM?
Okay. OM.
Sorry,
Yeah,
Trevor
thank
Eichler's here too.
Sorry.
Trevor. Okay, Trevor. All right, so I think I was generous in grading and I give full points if I see is almost correct, even there are some issues where I still give them full points, okay? So now some people, that's kind of make me sad that you cannot add numbers even. Like one student couldn't actually add 68. So 64 plus 4 is supposed to be 68 when you convert that binary to decimal. And somebody's added like 64 on this. Because the chart starts from 1, 2, 4, isn't it? It doesn't start from 0. 2 to the power 0 is 1. So 1, 2, 4, 8, 16, like that. So you have 64, then 4, 68. It's pretty simple on this one. The second question, the second binary to decimal. If you cannot do that, then how can I help to pass this course? This is very fundamental. Binary, decimal, decimal to binary. And if you don't get that correct, then you can't blame me for that. Convert machine code, yeah, to MIPS instruction. Most of them was good, but the next question, I particularly see, that's why I ask you, I spent quite a bit of time in the first lecture about learning how to follow instruction. I actually made a video and put it on YouTube. The instruction was convert the following MIPS code to hexadecimal machine code, not the binary code. Hexadecimal machine code, that very clearly said that there. So I give more points, 3 points each of this. And a lot of students, they don't do it, they just did it binary and then no hexadecimal. It's pretty straightforward. From binary to hexadecimal, just copy that. What is this answer key for the meter? What do you mean answer key? What key here? So I'm telling you right now. I'm going through it right now. The answer. So the question 1, answer was, correct answer was what? 1 0 0 0 0 1 0 1 0. So that's the first one, 1266 binary. And then the second one is 1 0 0 1000. So that's the binary to decimal to binary. Then from binary to decimal, first one was 174, second one was 68. And then machine code was, the first one was that number 3. The answer was SLTI and register AT, register T1 and 3. And the second one was load word. Yes.
I don't know if you're meaning to share your screen, but we don't see it.
Oh, I see. The I'm going to share the question paper. What's that? Yeah, the second was the OX8E46002 is load word. Is register A2 and then 2 and then parenthesis S2, not S2. But a lot of people put 2 after that. That's okay. I just take it as it is because you need to follow the instruction in the MIPS page and see load word how it works. So if you go back to that load word thing, let's look at that now. From slide, I think we have what there's the MIPS reference sheet. So it's saying that my screen, yeah. So if you see the load word, where is it? Store word, yeah, in the middle, load word. See that you have this RT and then RS and then that sign extension immediate. So that will be like this format. So this M, the memory. So you it looks like the 2, then you have a parenthesis and then $S2. That's the structure for the load word format. That's okay. I give points. If people have the register A2 and register S2 and 2, I gave them full point. I didn't deduct any point once there. So there's some important one. But a lot of people make mistakes on the number 4. They didn't convert to hexadecimal. And number 4A was OX 01285012. And then second one was OX 02538820. A lot of people have problem with this one. There's 2, for some reason. So if you look at the green shade, and you see this T2, T1, and T0 from here. T2 is what? T0, T1, T2, 8, 9, 10. So the 10 is T2. And then you have T1 should be 9 and T0 is 8. Basically 10, 9, 8. So as long as you follow the process, I just give points. Following the process is important here. So the calculation is not very important, but the process. And number 5, addition. Addition was some, so 0 plus 1 is 1, and then 1 plus 0 also 1, and then 1 plus 1 is 1, 0. So it's 1, 1, and then 1, 0. That's it. There is no carryover. Some people found carryover. I don't know how I got this carryover here because This shouldn't be any carryover. And this one, a lot of people did not do well. The 5SE and 2BE. So remember that way we learn it. What is my OneNote thing? I think it should be still there. That example we had. Few times, I think it should be there somewhere. Let me find it. Where we add the that's not it. I think it should be. No, fine. So this is the binary stuff. This is the addition. Just conversion. Recent. Yeah. So if you look at this addition, what we have done, remember? So you add this with that. So E is here, 14 plus 2 was what? 14 plus 2 is 16. So 16 is one hex. So we take carry 1 there and with 0 there. 16 plus 0 is 16. And then we add this 1 to the D. So D is 13, plus 1 is 14, plus 8 is 14 plus 8 is 22. So 22, you can write 16 plus 6. So put 6 there and take 1 up here as a carry. And 3 plus 1 is 4. 7 plus 4 is 11, is B. So like this. A lot of people had trouble with that. So be 86A, actually, 86A. The question we have in hand.
Professor,
Yeah.
are you using an application to draw? Because we can't see it if you are.
You can see my screen?
We can see the midterm, but are you drawing on it?
I'm not drawing, but I opened a drawn one, already drawn. So you can't see that.
Oh no, we can't see it.
Oh, maybe we have to share the whole thing. We didn't share the whole screen. Yeah. Now we can see.
Oh yeah, now we can see it.
Yeah, so this is the process that we explain in the class, that how you do this. So let's connect the that Wacom pad to that one. One more. And a lot of you got it correct, but still quite a few people didn't get it right. All right, so our question was 5SC to BE. 5SC to BE. 5SC to BE. There are other questions. Okay. So C is 12. C is 12. And E is 14. So 12 14 is 26. So you got 26. So you got 16 plus 10, 26. So you got 10, you drop 10 there. So 10 is A. So you get A. And then you go 1. Now the A is 10, so 1 is 11. And B is 11, it's 22. So 22 is 16 plus 6. We have it here. So you put 6 here. And then you go 1 here. 5 plus 1 is 6, plus 2 is 8. So it's 8, 6, 8. So that's the hex.
Professor,
Yep.
I'm sorry, I'm a little confused as to why you decide to split 26 into 16 and 10 specifically.
Oh, because 16 this is a base 16. So you need to split that number, 26, in terms of 16. So 16, and then you have leftover 10. So
Oh, okay.
you put the leftover here, and then this has become 1, and you go there, carry 1. As we did the other one here, same.
Okay. Thank
So
you.
here we add E to 2. So E was 14 plus 2 is 16. So 16 plus 0 is 16. So put 0 there, and 16 goes here, carry 1. And then we add that up. It became 22. And then we did 16 plus 6. So put the 6 there, and then carry 1. 3 plus 1 is 4. 4 plus 7 is 11. Put B. Similar. Very similar to this one. Are we clear now, everyone?
Yes, thank you.
That's very good. So it's very important. Hexadecimal, sometimes you need it, but where to use it? There's some use for hexadecimal stuff, but more use for the binary stuff, of course. Any other question from any other? 3A? You have question about 3A? Okay, let's look at 3A. Somebody has a question about 3A. 3A. So X 292. Okay, let's look at that. 2921003. 2921003. Let's add a new page. 21. Two nine two one. Two nine two 1 2 3 4 5 6 7 8. Okay, so that's OX. So this is the machine code given to you. Now your job is to convert it to MIPS instruction. MIPS instruction. So since it's given hexadecimal, so our first step is to convert it to binary. So in order to do the binary, we start from here. Let's say we have 32 bits. So 3, we use 4 bits. So 3 is this. And then 0, 0, 0, 0, another 0, 0, 0, 0. Yeah. Then I have 1, 1, 0, 0, 2, 1, 0 is 2. We have 9. So what is 9 here? So you have 1 0 1 1 1 0 0 1. That's 9. Then I have 2. So that should be 32 bit. Now in order to do this, you have to go this 1 2 3 4 5 6. This 6 bit, and then 1 2 3 4 5 bit, another 5 bit, and then we have from here we need 6 bit, and then so the shift amount is should be 0 there. So now you look at the reference sheet 001010, basically 10. What it says, what kind of operation. Here. So 1 0 1 0 should be in the end. Things here. Things here. 1 0 1 0 1 0. Is that our number? No.
I think it's SLTI.
Yeah, actually 0 0 1 0 1. So yeah, I mean it is, but we want to figure out where. This is SLT.
It's in the third block from the top.
Lower here.
One more higher.
Here. Move.
SLTI.
Yeah, SLTI 0 0 1 0 0 10. Decimal 10. This is binary 10. And SLTI. So this is how you find out from here, and then go to your. So this becomes SLTI. Oops. Then you need to convert all this RSRT stuff from that sheet. So now you get, this SLTI, and you go back here and see what's the format here. RT, RS, RT and RS. So RT and RS. So this is I format. So if you go here in I format, see RS first and then RT and then immediate. So RS and RT. So now you convert that. These two. So you see that 0 1 0 0 1. So go back to the sheet. Basically 0 1 0 0 1 is how much? That was 9. No. 1, 2, 4, 8. Yeah, it's 9. Still 9. And then you go back here. The 9. And you get
I think it's T1.
yeah, 9 here. T1. Yeah, correct. So right down here. And then I got this. This one. 1, 80. I mean, the whole thing not make sense much because I just randomly pick it. In terms of actual operation, it may not make sense, but that's the process. So you got that, and then this is 3, of course. And you have 3, the immediate. And 2 example instruction set computers. And then the gates, the NAND gates, it's like not and XOR, exclusive OR. So quite a few people, they have NAND gates, and I mean, they have this truth table, but no gates. And some people have gates, but no truth table, something like that. I mean, that's It's very straightforward, isn't it? Like if you look at that gate stuff, let's look at the example first, that way, a risk example. Okay. For this chapter, right here. For PC, MIPS, oh yeah, and processor. So that was the answer, like you put this two examples from here. And a lot of people struggle with that. I don't know why. I didn't ask about anything else. But
Oh, professor,
yeah.
when you ask like the examples for the risk, are you looking for like MIPS and PowerPC, or are you looking for like phones, like PS4? Like, are you looking for specific or?
No, really, just any examples. Like if you say PowerPC, I take it. If you say Apple Macs, IBM, I still take it as the correct answer. So, I mean, as a whole is PowerPC, but PowerPC has different kind. And then MIPS also has different kind. It's the Nintendo cable modem, cameras, Sony PS2. But whatever you say, if you say any name of any of this or PowerPC, MIPS, still correct. So that's I mean the example, actual example though, but if people say MIPS and IRM, I just got it. Give them a point. It's okay. Any question? Oh, for the gate, let's look at the gate. I open it yet? No. 6. So that was the truth table. We have a 2 input. Then NAND here, 1110, and the XOR 0110. And then if you draw an AND gate, or of course we have not gate here, but not gate, it's not NAND gate. Secret draw from here. Actually, the easiest is they use the software and then you put the truth table and they'll draw it for you. This is, you can do it in the exam time. So this is the XOR gate. And then this is AND gate, but you can make it not AND. This AND gate. We can put a not in front of it. You convert like this one. So it's simple gate I ask you to do, not complicated stuff. And it's good. I mean, a lot of people, I give them full points, so it's fine. But people who didn't answer all of them is a problem. And some people ignore number 6 or ignore some other questions. So that's, I don't know why, but all right. Maybe they ran out of time or something, or whatever. Any question from this? Any doubt? No. Okay, let's move on now to the next chapter. So this midterm is done. So we don't have to study those anymore. Because the final will be now on forward, whatever we have. Chapter 7 to 8, 9, 10. We have 4 chapters on. Very small syllabus, not too much. But my focus is like whatever you learn properly that you can remember, you can use it in the future course if you need to. I mean, there are. So, is there any the advanced course of computer architecture? I think you have one. Is it compulsory? Do you know? Anybody knows about it? Do you have to take? Do you
What
have
was
to
the
take
question?
it? The advanced course, that computer architecture course. I think another there, one more, the
Oh,
advanced level.
I can check. Hold on.
Is that compulsory for a computer science major or just optional? Check it out from the
If it's CSC 415, yes.
it says computer architecture.
Oh no, that one is after this one. It says we need to take operating systems.
No, that's the different course, but no computer architecture.
I don't see anything on this.
Yeah, probably is not compulsory. It's probably we call it elective. If you decide to take the advanced course, then you can do it. Especially like if you want to be a computer engineer, like design chips, then you can go through the route, the advanced course, and learn more about this chips design. And yeah, otherwise you don't need this. If you just become a data science engineer or just an AI engineer or just a developer building business applications or even networking, you don't need advanced computer architecture stuff that much. But of course, you see that like in the first chapter, why study machine structure is why this this one. This you see my you don't see my screen. That was the reason I studied machine structure. Compiler development. That's why they have compiler course for your operating system. Operating system course, low-level operating system. Yeah. So after this, you take this low-level operating system course, and then performance critical code, new hardware stuff, GPU design, multi-core development. That's the whole purpose of this computer architecture course, machine structure, we call it here. So if you're interested in this area, then you need to take that advanced course. Otherwise, you don't need to. So that's why they didn't make it mandatory for computer science. Okay. So let's, can you see my screen now?
Yeah.
Chapter 7, MIPS processor.
Yeah.
Let me look at if I make it available in the iLearn. 6 is open, 7 is not. Yeah, I'm opening now. Okay, so you have that. MIPS implementation. Then we have a video here. Put it on as well. Let's look at the video.
If you only list your vacation home on Airbnb, you'll get a couple who'll stay a couple of nights.
Welcome to the Progressive Learning Platform Instruction Breakdown and Data Path Tutorial. In this tutorial, we will show you the different types of instructions and break them down to see why they are different. We will discuss the 32-bit size that all instructions share. We will look at what a pseudo operation is. And lastly, we will follow a handful of the instructions through the processor's data path. As you can see in how we write our instructions in assembly, there are some similarities in the syntax for different instructions. If we look at an add instruction.
Okay, can you hear this?
Yes, but it's not that clear.
Okay, you can hear. I mean, watch it one more time on your computer as well. So let's continue a bit because
For example, we know that there are 4 parts of its syntax. The first part being the instruction name, the second being the destination register, and the third and fourth being the source register. When the instruction is read by the assembler, these 4 fields define values in the instruction that determine the path that the instruction takes through the process. Here is another way to write the same instruction using the register numbers rather than the name. This will help demonstrate where they fit into the instruction breakdown. In the case of an R-type instruction, the 32-bit word that the assembler turns our code into contains 6 parts or fields, each necessary at different stages of instruction execution. The first field are 6 bits for the opcode. The opcode is part of what determines which processor components will be utilized while performing the add operation. The assembler knows which opcodes to use for which instructions, and the opcode controller in the processor knows how to handle each opcode generated, so we never have to manually manage what value is stored. After the opcode, the 2 source registers follow, each 5-bit. Then there are 5 bits for the destination register. 5 bits is used for all parts of an instruction that stores a register number because the possible values in a 5-bit number are 0 through 31, which is exactly the number of registers in our register file. Next, we have 5 bits for the shift amount, which is not used by add, and therefore would just be 0. The last field, function, is used to define which function will be performed on the register. This layout is an R-type. Being that the bit pattern used by an instruction is based solely on how the instruction needs to be processed, we can see that whether any other instruction is an R-type is not because of its logical functionality, but rather which components in the processor to utilize. There are 3 total types of instructions, the others being I-type and J-type. While some similar operations are of the same type, add, subtract, for example, we have to keep in mind that their logical operation is not what places them in the category. An add immediate, for example, is an I-type, and so even though an add and an add immediate both add 2 numbers, it is the source of those 2 numbers that gives them a different type. The determining factor for what places them in the category is solely based on their encoding. Add and subtract,
I think I need to
if the
go to the
instruction set
data pack.
architecture wasn't RISC, there would likely be an instruction that handles this directly. But the RISC paradigm and its name aims at reducing the number of instructions in the instruction set. This is the reason that pseudo-ops exist. Another pseudo-op that we've used frequently is no-op. There really is no hardware instruction to perform nothing. So the no-op performs the instruction shift left logical to the 0 register, contents of the 0 register 0 times. This is what we use to fill branch delay slot. The pseudo-op doesn't come by through the data path.
Let me show you this.
As you step through how each part of the instruction is utilized.
I think sound is pretty low, so you can actually watch your own time.
It's important to note that the hardware does not execute the instruction in the step-by-step fashion that we do. These steps will be happening concurrently, and inherent delays in the hardware will ensure that data is where it needs to be when it is needed. For this R-type step through, we will use an add instruction. The first thing that the processor must do with this in all instructions is to load the instruction from memory from the address stored in the program counter. This address is also used to calculate the address of the next instruction, which we will discuss later. From here, let's break this instruction down and see how each part is utilized. Let's first look at the opcode. It's 31 through 26. As you can see, this is what goes to the control unit, which decode the bits and essentially set up which path will be used. The reg destination needs to be sent a high signal because this is what tells the multiplexer that feeds the register file that 3 registers are being used. Since we have an ALU operation to perform, addition in this case, the ALU op must also be set to high to signify to the ALU control unit what data needs to be passed to the ALU. The control unit will also have to send a high signal on the reg write to notify the register file that there will be resulting data that needs to be written to a register. The jump and the branch must both be low signals since neither of these functionalities are being used. Mem read, mem to reg, and mem write will all be set to low since there is no memory manipulation in this instruction. Lastly, ALU source will be a low signal. This is what tells the MUX that feeds the second argument to the ALU which piece of data will be utilized. The next part of the instruction, bits 25 through 21, indicate which register's data will be read and used as the first argument passed to the ALU. For this walkthrough, we will say that there is a 5 stored in this register. Bits 20 through 16 indicate which register's data will be read and used as the second argument passed to the ALU. We will say that there is a 3 stored in this register. For bits 15 through 11, since the control unit sent a high signal to this MUX, will indicate which register will have the results of the operation written to when calculated. Bits 5 through 0 are passed to the ALU control unit to signal to the ALU that an addition operation is needed. This is the function part of the instruction. Subtraction, for example, uses the exact components as addition and therefore has the same opcode. The function gives us a way to keep everything the same and only change what the ALU needs to do. Now that we can see how the data path is set up by decoding the instruction, we can look at what happens to the result of the operation. We already saw that a low signal is sent to the data memory, so that will not be utilized. And also that a low signal was sent to this MUX. So we now have the data that needs to be written and the register that that data needs to be written to. Since the reg write was enabled, the data will be written to that register. We have now seen all of the components used to execute an addition or R-type instruction. Though there is still one more thing that needs to be discussed, which is getting the next instruction in the program. We previously saw that when the address of the next instruction is read, the address is also sent to the input of an adder that adds 4 to it. Since the system is byte addressable, adding 4 to the current address gives us the address that is 32 bits away for the next instruction. Since neither of the two MUX along this path were sent a high signal, the address plus 4 is what gets loaded into the program counter as the address of the next instruction. We will now look at a different type of instruction to see how the hardware handles it differently. Let's look at a jump or jump to label.
Okay, so you look at that, what's the own time? Maybe a few times to get this. So it has a link from the island, so you can do it on your own time. Fine. So let's look at yeah.
Is stuff like that going to be on the final?
No.
Okay.
No, that's a bit high standard test. No, that's not. Just to give you a test how it may look like when you go through this MIPS process of design, this chapter. So you can, if you're interested, you can go in deep and then try to figure out everything, how a R-type instruction works and how J-type or I-type works through that circuit thing, the multiplexer they use. So it has visualization, so you can see that lighting up all this. I don't have those kind of software or anything like that. So let's look at this basic concepts about data path. So we learn about stuff like registers, memories, glue logic, connections. We'll learn about this. And control is active part of the system, directs data path to perform necessary action. That's the definition of control. Control is active part of the system, directs data path to perform necessary action. The goal. Design a simple CPU to support a subset of MIPS instruction like R format, load, word, stored, or branch. This kind of operation like add, sub, and or SLE. That's an operation for simple stuff. So we are trying to learn how exactly it works, how to design a CPU. You can perform those kind of operations. So that's the goal. Each instruction completes its one cycle. Cycle must be long enough for slowest operation to complete. Okay. What is the advantage? Now, these things to remember for the test. Simple single cycle implementation. What is the advantage? like for the simple single cycle implementation. Simple cycle in design is relatively simple, of course. Disadvantage, inefficient. Fast instruction have to idle to wait for slow instruction. So fast instruction have to wait until they finish the slow instruction. So MIPS instruction formats, page 136, figure 220. If you have the book, you can see it. That format, we already learned about formats, R format, I format, and J format. The major component of registers, we have the read registers and write registers. Write data, read data, and then program counter. Okay, so R0 to R31 registers. Okay, major components in the memory, instruction memory and data memory. So two types of memory, instruction and data. Major components in arithmetic logic unit, ALU. So ALU itself has this kind of operation. Okay, you have 000. This code means AND. 0001 is OR. 0010 and so this is not the function code. It is different than function code. This is only for the ALU. So this code is different than the function code that we have on the 32-bit. So this is the internal to ALU. This is different. You see, 00 is AND and 001 is OR. 010 is AND. 0110 is subtract. Set less than 01111. 1100 is NOR. So 0 if ALU result equivalent to 0 and 0 equal to 1, else 0 equal to 0. Processing and arithmetic logic instruction, R format, all register operand. So R format, as we know that you need 3 registers. So we have this add the operation code, and then you need 3 registers, RD, RS, RT. So RD first, and then RS, RT. So step 1, what do you do? Instruction memory. Step 1, you fetch the new instruction. Step 2, you decode instruction. So get RS and RT. Step 3, execute add operation. So you have an adder, you execute that add operation. Step 4, write result to the RD, the destination. Write result to the RD. And the first next instructions, you have program counter equal to program counter plus 4. Why 4? Because they use 4 bytes means 32-bit. So it's the next line basically on the register. So use PC plus 4. Okay, then what do you do? Basic operation of ACE triggered logic. You have this the D flip-flop in, and then you have a clock, and then you have the output. And then there's a timing diagram, they call it here, in, out, clock. And ACE triggered logic is another D flip-flop timing diagram. Then load word instruction, that we had one load word instruction, how it works, like how you can build the circuit for that. Test the instruction, decode instruction, get RS. Because load word, you have RT and RS, and then you have this integer number, 4 bytes. The next line, upper or lower. -4 is like you go up, and +4 is go down to the registers. So the first decode instruction, and then step 3, when you do step 3, you calculate address, RS plus immediate. And then step 4, you read data memory. And then step 5, you write data to RT. Target. So from an instruction goes into lower arithmetic logic unit input. They use this. Now from an instruction, okay, then we have the 16-bit constant goes into LU. Then you use the multiplexer and all this. Can't just can't remember it like this. You have to just try to understand it, like how this process works. And if you watch that video, the link I give you a few times, then you may figure out how this thing exactly works. ALU result to write data to of registers, RD to write register of registers. Load instruction, data memory, read data to write data of registers, and RT to write register of registers. Solution, add multiplexers for selection. So multiplexer to do this read and write stuff. And then branch that J format. So you have branch equal to RS and RT and the target, RS minus RT. If RS minus RT equal to 0, program counter equal to target. This is how you draw the simple data path to support MIPS subset. So you see that in the video that they have this operation diagram, and it's pretty nice. They have a color coded so you can see how those instruction works. Both ALU source, ALU op, memory read, memory write, memory register, and all this operation here. You have this ALU operation command, load word, store word, and branch equal to archive. This instruction, then operation instruction is this. We have ALU function, ALU control. Just read through this a few times and watch the video, and you'll get the idea. You'll not be tested in this kind of stuff. Different parts of instruction were determined control signals to be ALU op determined by opcode. Type, load, branch, all this stuff. Determining control signals for each instruction. All right. R-type instructions is another figure how it exactly works with the simple MIPS implementation. You have a controller, you have adder, you have multiple adder, then you have the multiplexer. Adder and multiplexer. Branch equal to three different circuit, three operations, and then jump instruction. It's another circuit. Then you talk about performance. Memory units, ALU, register 800 PS and register 800 PS. So we calculate this performance. Cycle versus clock rate. So suppose your computer has 1 gigahertz clock. So 1 gigahertz means what? 10 to the power 9 cycles per second. And one cycle is 10 to the power minus 9 seconds. And then 1 nanosecond is 10 to the power minus 9 seconds. They call it a nanosecond as well. So one cycle is 1 nanosecond per second. And then 1 picosecond is 10 to the power minus 12 seconds. It's very tiny. That's the clock rate. In gigahertz, 10 to the power 9 cycles per second. Now we learn about pipelining. It's a very simple concept, but it's very useful, especially for this CPU calculation when it does the calculation. It's very, so that is as a metaphor here about the pipelining. Okay, doing laundry in 4 steps is 30-minute steps. So wash, dry, fold, and put in closet. Let's say each item takes 30 minutes. Total is 2 hours. Now each load takes 2 hours. Okay, 4 loads take 2 times 4, 8 hours. But can overlap steps like an assembly line. So what happens if we have like 4 bunch of clothes, and we go through one by one, it will take you 8 hours. But if you use the pipelining technique, that will save your time. How you can use pipelining technique? like fresh load. So you have like the poor load ready clothes. It's like poor basket, you have poor loads of clothes. Now take the basket one and put it in the wash. And it will take 30 minutes. In this 30 minutes, you cannot do much. You cannot do anything else. So then after 30 minutes, you put those clothes into dryer and then and go to the basket two and put it in the washer. So this second 30 minutes, you're drying and also you're washing, second lot. Like that, if you use this pipelining technique, like you're folding one and then you're drying another one. And then like this, it will save your time when you finish the full load. So that's basically the idea about this pipelining. So you can use the same technique actually in processing in simple MIPS pipeline. So you have instruction, the paste instruction first, and then you have this decode, then you have execute, and then memory access, like memory read, and then memory write, like write back. So you have these 5 steps to do. And you can, so you have lots of instruction to process, lots of things to calculate. Then you can use that pipelining technique and implement that in your design. Then you save time. So that's why you see that the processor, we have this modern processor, is very fast. They can do like millions of transactions in seconds. How they do it? They use this pipelining technique. They use the resources efficiently, basically. So you need to learn even in real life, like when you do things, like when you work. So you work, you get paid, and what do? You just shop and spend all your money? No, you do other thing. You invest, and you invest in different field, different area. Maybe you invest in real estate. Maybe you invest in stock market. Maybe you invest in other startup business. It's a lot of things you can invest on. So that's the kind of a pipelining technique. Like instead of just investing all in one, you actually invest in multiple items and then that may save you time. Like you may make money. Maybe one item will lose, another item may make, another item may make money. So in the end, it's like an index fund, the average. So they may, in the end, you may averagely make money. So this technique, this information page and decoding, executing, memory read, memory write, write registers, if you use this pipelining technique, it will save you time. Can overlap steps, pipelined, MIPS implementation. So there's an example here, like the calculation. What difference? So you have a load word, it takes 200 picoseconds. Register read 100 picoseconds. ALU operation 200 picoseconds. Memory access 200. Register write 100. So total is 800, like this. So store word, hard format. So it saves you time. That's all they're showing you here. If you use pipelining, it will save you time. All right, so that's the example. And what else? Now, pipelining has some issues, okay? It has a lot of hazard. You have 3 types of hazard. You have a data hazard, control hazard, and structural hazards. It has some issues when you pipeline. It's not as smooth as you think. So maybe you're waiting for something to be done to start on the process, but that thing's delays for some reason. And then you cannot process the second step. So you have to wait for that. So you need to remember these 3 types of pipeline hazard. And it will come in the test, maybe in final, some of them. So data hazards is instruction uses the result from a previous instruction. And if this instruction is not coming, the data is not coming, then that's a hazard. So load use data hazards. This is load word. If you're waiting for something and you can't do that because it's not ready, then that's a hazard. This kind of hazard is called a data hazard. Okay. So we will look at that as well in the next class. So I'll explain more. Code scheduling to avoid load use installs. So how do you avoid this? So the load. See, that's in the picture here. Sometimes a compiler can reorder or reschedule an instruction sequence to avoid load use stalls. So have T2 here, T4 load word, and then install. It's 30 cycles, then you can make it in 11 cycles. You can reduce 2 cycles to move around things. See, so load word we move from here to there, the third, and that, and then add, send it to the add is there. So store word, instead of store word, you put this add instruction there, and this will save you 2 cycles. So this is an example. You can save time. Control hazard, a pipeline hazard caused by an instruction that changed the program count. The conditional branch and jumps. So when it changes, that creates a hazard. That's a control hazard. So it's a branch equal to an example. Need to know as soon as possible. So branch target address for branch equal to. You can try to calculate both in the instruction decode stage, but installs are often necessary. So you can also try to predict branches. In general, branch and control instructions are difficult for efficient pipeline operation. This is the control hazard. And then I have another hazard, the structural hazard. The structural hazard occurs when the hardware component is needed by more than one instruction in the same cycle. So this is a resource conflict. So same resource cannot be used at the same time with the two. Use it. So you have to wait for one to get it done and then move. Current MIPS pipeline has no structural hazard. But suppose we decide to combine instruction and data memories into one memory, and then on every load word or store word, when we access data into the memory state, there is a conflict with the paging state. This would be a structural hazard. The pipeline has to stop. So we started these 3 hazards, and with example actually. So we'll talk about that even more in the next class as well. So this is the pipeline. Simple mesh data path divided into stages. So it's a data path. Need pipeline registers between each pair of stages. At rising edge of clock, the new contents go through logic, new contents propagate to input next register. So it's talking about this circuit again, load word, store word, the decode phase, execute phase. So it's phase like 5 phase, how it goes through. So if you watch that video, it will be clear and read through a few times, then you'll see what's going on here. You don't have to memorize anything, just try to understand all this instruction. You see this load word, so add, load word, add, all this. Cycle 1, cycle 2, cycle 3, 4, and I have 5. So 5 stage. Now you can simplified view of pipeline control. So this is the simplified view. Then you have this different stages, what kind of calculation goes on, and then performance. We'll talk about that in the next class, the performance part and the review of this control hazard again. We have time, we don't have to rush. So it's very simple, the pipeline, the performance, we'll learn more about this. All right. So go through the video, learn that, and have a test how this circuit design works. Simple MIPS instruction. Okay.
Oh, Professor, somebody
Yeah.
earlier asked if there's gonna be like stuff like on the midterm we had recently. Are questions like that gonna be on the final?
Question about the control, the hazard, yes.
Oh, like
But not
Like
this circuit, not the logic gate for this MIPS implementation.
oh, okay.
No, I will not ask you to draw a circuit for R-type instruction process. No. No, that's too complicated for exam.
Okay.
Yeah, no. Sorry about too much. No, I'm not going to that harsh.
Professor?
Yep.
So will the final include everything that happened after chapter 5, I think, was the last chapter we covered in the midterm? Would
No,
the final
last-
just include the last ones or everything?
Last chapter was 6.
Okay, so will the final include chapter 6 to whatever chapter we finish?
No, we'll cover only from this chapter, like chapter 7 to 10. That's it.
Okay, all right, thank you.
Only 4 chapters.
Okay,
Don't
thank
worry.
you.
Very simple, okay? Just focus in the class, and you'll do well.
Thank you.
All right, so see you in the next class. Just watch the video and read through the slides and look at it in next class.
Thank you.